We will start with a small change in our exponential decay model. So what was our exponential decay model? Basically was a barrel. You had a pipe attached to that, and it will be a draining barrel model. So if you can set the barrel initial volume to about 60 liters, that will be the size of the stock.
Yeah.
And the little hole that we make at the bottom of the barrel would have a drain fraction of 0.1. And basically it means that the barrel is draining at a rate of 10% of volume every minute. So our units will be minute, and unit of the barrel will be liters. Instead of months, make it time units will be minutes. That's right. And start time we can make 50 minutes. The stop time. Yeah. Because we want to run the simulation for 50 minutes. That's why. And now, as you can see in his model, so we have barrel, which is how many liters did we say? About 60 liters.
60 liters,
and the flow is amount draining per minute. That's the flow. So flow 1 can be named as draining per minute. And the converter can be called drain fraction. If you can just run the model. Here, I will give one thumb rule, which I had given earlier also for doubling time. And earlier we had said doubling time is 70 divided by the rate gives the doubling time. And then in the draining process, you will often hear of something called halving time, HALVING. And halving time is basically 0.69 multiplied by 1 upon the drain fraction, or divided by drain fraction. So 0.69 divided by drain fraction, which is 0.1 here. That's right.
Yes. Yeah.
So now what I was saying is we can quickly calculate halving time. Now halving time would be 0.69 divided by 0.1, which is 6.9. So in this case, approximately every 7 minutes, the model should drain half. So can we cross check that whether that is happening? What happens at 7 minutes? How much is the amount remaining?
At 7 minutes is 30.
Yeah.
Oh, sorry, 29.5.
Exactly. So 6.9, at 6.9, it will be about 30, starting from 50 meters. Okay. Now, if you take another 7 minutes from here, it would be half of 30. That is 15.
14.
So 14 minutes, it will be about 15.
Yeah.
See, take it to 14 minutes, or really
14.5, almost 15.
Yeah, I'm only trying to say is that all the time we should also have some small little ability to simulate these processes in mind. So there was a doubling time. Doubling time is whatever is the percentage rate of growth, then divide 70 by rate of growth, and that gives you doubling time. And similarly, if you divide the drain fraction from 70, it will give you halving time. Is everybody clear about halving time and doubling time? Can I have a bit of a sensing from people? But at this moment, just remember the thumb rule, which is 0.69 or 0.7 for halving time and 70 for doubling time. See? So if your rate of interest, the rate of interest that bank is giving is say 10%, then the money that you put in bank will double in what time? That is 70 by 10, that is 7 years. Okay. So that's the doubling time. When it comes to halving time, see, that is on an exponential decay, then we say divide the draining fraction, or divide the fraction whichever is the rate at which it is draining, from 0.69 or 0.7, and that will give you a halving time. And you will often see governments talking about it now in real time with Corona. One of the things with COVID models you will hear is what is the doubling time. Now for India, doubling time is 11 days, for example. I'm just giving an example. So if you look at the number of total deaths today, and if doubling time is 11 days, then 11 days later, these deaths will double. See? And once you have that, then you can know at what rate the deaths are happening on a daily basis. So if 11 days is the doubling time, then 70 upon 11 is approximate rate of growth on a daily basis. So now, if you divide 70 by 11, you get a figure of about 6.5%. So whatever is the death amount, total deaths today, they will increase by 6.5% tomorrow. However, howsoever number the cases are there today will increase by 6.5% tomorrow. And 6.5% of today's cases. And day after tomorrow, the number of cases would increase by 6.5% of the total cases tomorrow. And that is how we achieve. And then you will see in 11 days' time, they would have doubled as compared to tomorrow, as compared to today. So that's doubling time. And same thing is with halving time. If there was a exponential decay, and when the COVID starts dropping down the cases, they will start talking about halving time. Now they are talking about doubling time. And here you see there is a drain fraction. Drain fraction basically means how much percentage of the barrel is getting is the water coming out from the amount of water which is in the barrel. So amount of water in the barrel is 60. In 1 minute time, in the first minute, 6 liters will drain out. In the second minute, 10% of remaining 54 liters will come out. In the third minutes, again, remaining amount of water will come. That's why it is, you can see the graph which is there. It is fairly steep in the beginning, and then it starts sort of flattening out. So this process is actually, if you look at it, it is a balancing loop already. It's not a compounding growth. It's a balancing loop. It's called exponential decay, but the loop is balancing because it is a goal seeking loop. It tries to come and comes to zero here, and it never really reaches zero if you go by algebraic expressions, because it will be half of it, and then in a finite time half of the barrel will drain, and then in finite time another half of the barrel will gain. So it will approach zero. It will not get zero. It tends to zero. Has it become a little bit clear? Fine. So that's fantastic. That's a big thing gone. A very big understanding is understanding of halving times and doubling time, actually, I think. So we go on to the next bit. Now, can you use the model of the data and verify halving time of the model? I can see that you have made a graph table below, a table below.
Yes.
So if you can show us the table and see what is the halving time, we can, let's confirm it. See,
60.
see, we
Yeah,
started
it
with
is here.
60
7.
liters. So at what time does it become 30 liters? It is just shy of 7.
Yeah.
Okay. So that's when it becomes 30, and then we can go down further, and you will see at about 14 minutes, it would have drained half of that,
Yeah.
okay, which is about 15. See? And this is a thumb rule, so we are only giving you approximation.
If change DT, I think it will happen.
What is the DT? DT should be 0.125 if you put DT. Instead of
If
zero point
we put
0.5,
one
put
five, yeah,
0.125. Yeah, because if
it will
we
happen.
integrate it more often, it will become more accurate. Yeah.
Just run it again.
And also, once again, basically what
Yeah,
DT
now
means
see.
is how often is the Stella computing the model. That is what DT is. So now can we see the halving time?
Yes, sir. Now we can see here at the seventh minute it is 29.7.
Yeah, okay, fine.
Yeah, here.
So that we have clarified here. So we can use the data and verify that halving time of the model matches what you would expect based on the drain fraction. Okay.
Yeah.
Okay. And now we imagine that we have a second barrel with exactly the same drain hole and therefore same drain fraction. Okay. So size of the hole is same, fraction is same, but the hole is drilled higher up the side of the barrel so that when the barrel is drained, there is 5 liters of water left. How will you model this? See? So what we are saying here is that now imagine the barrel which was there earlier. See? You have a hole which is drilled higher up and lower hole is sealed off, and you've got the new hole so that there's 5 liters of water remaining in the barrel. And if we want to use the same model, how will we model that? So we start by copying this model and then we will modify the model. So
Yeah, yeah.
yeah, you can just copy the model straight away. Okay. And then what will you do? So basically, when the barrel is full, there are 60 liters of water with 5 liters that will remain after the draining is done. Okay. And that means there are how many liters of water in the barrel which will be drained out? If somebody can tell us. Yeah, 55 will 55 liter of water is there which will drain out. Actually, the stock in the amount of water in the stock is 60, out of which
Mm.
only 55 will drain out. So stock will still be 60.
Just a minute. 60. Yeah.
But out of this stock, we should only drain out uh, 55 liters, and 5 liters should remain in stock, and that is what the new graph should be. See?
Yeah.
See? So subtract 5 from 60, and that makes your water in the barrel. No, that doesn't make the water in the barrel, Behram. What it does is that is the amount of water which is available for draining out. And the draining process should stop when 5 liters of water is remaining in the barrel. That is what we want to simulate. So now let us see how we can do that. So drain fraction is like it was earlier, okay, 0.1, see, because the size of the hole is same. See. So drain fraction 2 is 1. And now we break this connector from here, and what I suggest is put another converter here. That's right. See. And let us call this converter as the difference, and put one more converter to the left of this converter and call this final volume. So final volume is 5. See, we can join these also. Sorry, we should have joined this. Yeah, you can make it 5 and join it here. Okay, hold it here before joining anything else. Basically, we have a converter now of difference, which is taking one feed from final volume and the other from barrel 2. Okay? And what in effect is we are doing here is we are comparing the volume of water in barrel 2 versus our final volume. That is what this will do. So how will you compare that? And that is what Behram says, subtract 5 from 60. That will do it. Okay? So that is what is happening here. So let us subtract that and click it. Now, basically, when we start subtracting, when the amount of water in the barrel will become 5, and this is 5, so 5 minus 5, this will become 0. As soon as this becomes 0, then you see the magic of what it will do. Let's connect this to draining 1. Let's connect difference to draining 1. Great. And let's get draining 1 into the equation. And draining 1 in equation is quite straightforward. Just multiply by the, yeah, delete this first equation, which was already there. You may have to first, yeah, okay. All right. So now this equation here, drain 1, is same as the earlier equation draining. So when we said draining, if you see in the top diagram, the equation here was amount of water in the barrel multiplied by drain fraction. Now here it will be amount of difference multiplied by drain fraction. That is the new equation here. See? And what will happen here in this equation is, if you look at difference, when the barrel volume becomes 55 liters and the final volume is also 5 liters, then it will become 5 minus 5, the difference will be 0, and that's where the draining will stop by itself. Leaving the 5 liters in the barrel. So let's see what happens. That is how it should work. Okay, you will have to change the. In fact, somehow, if we could not reset and have the model say both, you should not have deleted it. Put both the things.
Yeah, yeah.
Yeah, don't delete. Just put both and run the model. Okay. Now you can see. Can you increase the size of these if you go back to the graph? And actually, if you click the graph, double click it, and go down and increase the weight of the arrow key. It is
Dash
dash
dot
and dot. Make this also bold. That is solid.
solid. Yeah,
And there would be thickness here. Thickness is 1. Make thickness 2.
yeah,
Yeah, so that will increase the weight. Okay. And
yeah.
same thing you do for the bottom one also.
I'll select this
Okay. Yeah. Yeah. Now you can
and
change.
then change it. So make it two.
Yeah. And
Solid.
I am deliberately taking a little longer here for these processes because it'll be good if I can coach you to do this very gently of how to make the graphs little better, little more useful. See? And that just adds to the final product when you are going to make it. So it's not really wasted time, but you can see how these things are done. Lots of these little nuances of Stella are missed out in our excitement of making models. Okay, see. So now, has everybody understood this process at least? Any sensing? Now you can see the barrel 2 is, now we see the barrel 2, which is red line, okay, is showing certain amount of water remaining, and how much water is remaining in the barrel. That is what it
5 point.
shows, about 5.36 liters at the end of 50 minutes, and it is approaching 5, whereas the bottom barrel is gently approaching 0. Any questions on this so far? Let's experiment a little more. Now, if the hole was drilled a little higher, now what I would ask you to do is, if the hole was drilled higher, which means if you can change the final volume to 10, and let's run the graph, make it 10. Yeah, now run the graph. Don't change anything, just run the graph. And now make it 20 and run the graph. Already 29
Mhm.
minutes. Okay.
I'll change it to 20.
Yeah. And you can see that is how the model is behaving. Now, another thing you can do is you can straight away just change continuously, because the model is running in what we
Should I
call
change it here itself?
live mode. Yeah, drain fraction ke upar utha ke you can change from here, or you can change final volume from here. Okay. Yeah, here itself you can change. Exactly. See? So because Stella starts running in what is called live mode, and you don't have to go clicking on the panel again and again, you can just keep changing it from wherever you are. So you can see that happening.
Or
Okay, now,
shall we check the comparison in causal lens?
huh? Not yet,
Okay.
okay.
Yeah.
But what we want to do is we want to see something else. Huh? we want to also compare the halving time, and we said
Mhm.
the halving time is dependent on drain fraction. Okay, now let's
Yeah.
change drain fraction to point. Now here, if you see, in both these cases, halving time will be same, whether it is stopping at 5 liters, it's stopping at 10 liters, whatever, halving time is same because drain fraction is same. But if we change the drain fraction, okay, you will immediately see there is a change in halving time. So let's change the drain fraction and see if there is a difference on halving time. We can compare that also. And can you tell me what is the halving time now? Which drain
Now
fraction have you
for
changed?
this one, the second one,
You have second
barrel 2.
method, make the drain fraction as something solid, which is zero point 0.2 or something, so that we can calculate it more easily.
Yeah, point 2.
Okay. So now if it is zero point 0.2, 0.69 divided by zero point 0.2 gives me 3.45. Okay. So approximately 3.5 minutes would be the halving time. Yeah. Now see the halving time has changed from to 3.5 minutes approximately. You can see here.
Yep.
If you see on the right hand side of the left hand side of the barrel, those are the minutes, and you can see from 60 it becomes 30 in about 3.5 minutes.
Mm.
Is that okay? Is has have people seen that? So basically, let us now make a generic model out of it, see, of what we will use in many other things. See. Uh, get rid of these tables from here, Girish. Okay. So now let us make a generic template model out of this. So if you put a stock, take this stock a little to the right hand side, further right, because we want to make a generic. Yeah, that'll do. See.
Yep.
Now pick up a biflow and push it in the stock. That's right. Now make a converter and put it just above the cloud or between cloud and flow one. Yeah. No, further down, further down, further down. No, down, down. Yeah, somewhere here. Not so down. Anyway, see. And put another one more converter we will need here, somewhere here. And now we call whatever what you are saying converter one, we call it rate of growth or decay converter. The converter one is rate of growth or decay. See? Then we call converter two the gap, and we will have to put one more converter, see, above this stock somewhere, and further above the above stock and further down the gap, which will be called goal. Yeah, somewhere here. It is goal for stock. You can write here goal for stock. Goal for whom? Goal for stock. Okay. See?
Sorry.
Now join the converters. See? First join stock to gap and goal for stock to gap. Again, here I will emphasize that what would be the equation for gap? Equation for gap would be stock minus goal for the stock. That would be the equation. Stock one minus goal for the stock will be equation, which will be guiding this. And then from gap, you put the arrow to flow one.
Just a minute. Sir. First equation is stock minus goal for stock.
Yeah, exactly.
Mm,
Isn't
mm,
it?
mm, yeah, yeah. Now from gap to
Flow one.
flow, flow one.
Okay. And rate of growth or decay to flow one.
Yeah.
So here the equation would be gap multiplied by rate of growth or decay. And you can put,
Mm,
yeah, cancel that out because it is just, no, first put this red cross, you cancel it.
just a minute, sir. I think I need to put something here.
Yeah, you have to
Gap,
put some
gap,
rate of growth there.
gap into rate of growth.
Yeah, exactly. That's the equation.
Um,
And here you put any value, point 0.1, point 0.2, point 0.3, whatever is your rate of growth.
Point one.
And stock one, you will have to put some figure there, initial value. It could be 0, it could be 100, whatever you want to adjust. Okay.
Goal of the stock.
Yeah, whatever value you want to put any value you like.
Yeah.
Okay, so this becomes the generic diagram for stock adjustment because it is goal for stock and that is how the stock is adjusted. That is what we say. Or for goal seeking behavior of anything, that is what we will do. Okay.
Yes.
So I think, has everybody understood this much? If you have understood this, then there should be absolutely no problem doing last week's problems in which we gave last week's model. If you go back, which was about changing capacity, production capacity, capacity and goal, etc. Quick 5-minute question answers, and then we can end this.
Stop sharing now.
Share the screen. See?
Uh,
And we will go to questions. See? Please use Q&A mode. If you type questions there, I will be able to pick them up on the screen.
they will truly understand if I have understood it once I start implementing it.
That is very true because one thing I'm saying repeatedly with modeling is it is one thing understanding it on paper or on when we are projecting it like this, see? Because the first understanding is you are saying, okay, what Girish is doing makes sense and it sort of works. See? However, I can tell you we have to make the model several times before we start grasping what it is. And even now you can see us fumbling after 20 years of modeling. So that is true. And that is why we really want you to practice what we are saying on the website. And the more you model, better you become. Fine. So I think because we are already on 45 minutes, we will say bye bye to you and we will announce whenever is the next session.